Hi, Lawrence.
Hi, it's nice to see you again, sort of.
Nice to kind of see you again. We were on not long ago talking about your book, A Universe from Nothing, and since then, it has made an appearance on the New York Times bestsellers list, unless I'm mistaken. Is that right, Lawrence?
You're not mistaken. I think we're both not dreaming. I'm very surprised. It's appeared the week it came out. Yep.
Now, some people might say it's a coincidence that first we talk about it on Blogging Heads and then it's on the New York Times bestseller list. I don't think so, Lawrence.
No, I clearly see, and you've convinced me. I clearly see it was meant to be, and definitely you're the opinion maker that I hadn't realized you were.
We drive the memosphere.
Yeah, great. No,
so congratulations.
Thank you.
Now, last time we focused. Oh, I should say that you're a famous physicist too.
Thank you.
And you just got some honor, right? Didn't you just get an honor aside from the Times bestseller?
Oh boy, okay. Thank you very much. Yes, I just heard the day after it came on the bestsellers. I just heard that I'd been awarded from the National Science Board their Public Service Award which is a national award for science education, and I'm very honored by that.
And that's a significant honor, I take it. And you would not take advantage of my ignorance to claim that it's significant when, in fact, it's insignificant.
I think it's very significant. My mother asked me if any money came with it, and that, frankly, I don't know. But I do know...
the hallmark of significance, I'm afraid, is money, Lawrence.
I do know that there's a fancy black tie dinner at the State Department to honor it. So at least they've got that. I've got that going for me.
Well, tell Hillary I said
hello.
Avoid a war with Iran.
Okay.
So anyway, last time we talked about the subtitle of this book, Why There Is Something Rather Than Nothing, and that led us to do a lot of talking about what that means and what nothing means.
Sure.
This time we were going to try to, although it wouldn't shock me if we got drawn back into philosophy, we're going to try to talk a little about some of the more kind of scientific parts of it. Although I've got to say that a lot of the interesting things in this book that are science kind of draw us back toward nothing. For example, the idea that, as you put it, quote, most of the energy in the universe resides in some mysterious, now inexplicable form permeating all of empty space. That's an intriguing thought.
Absolutely. I think it's one of the most intriguing thoughts in modern science. In fact, it probably is what motivated me to write the book. So you're right. I think that's the reason the book is called what it is. I think we will continually get drawn back into nothing. But let me just start out by elaborating on that, if you want. I mean, a little bit.
Sure.
Because I want to make it clear how utterly inexplicable and weird it is, if it didn't seem weird already. And that is.
Now, before you elaborate, can you answer one question?
Sure.
I gather that this is a different, but possibly related issue, but a different issue from the so-called dark matter. The evidence that there's a bunch of kind of matter out there that we can't detect. Is that
absolutely? I mean, dark matter was plenty weird enough, and I've spent a large part of my career trying to figure out what it is and proposing experiments to detect it. But dark matter is nothing compared to dark energy, as we call it, because dark matter is just stuff. I mean, it's stuff like you and me. It's just we think it's made of a new type of elementary particle, which is fascinating, and it's going right through your body and my body, even as we talk, and so we can do experiments.
But we can't directly detect it, but we can infer that it must exist. Is that it?
Well, so far we've been able to infer that it must exist, but in fact we think we can directly detect it. And in fact, one of the things I'm very proud of is that I propose many of the experiments that are now going on to try and do that. If it's a new type of elementary particle, then it's not just out there. It's literally going through both of our rooms as we talk, and we think it interacts so weakly that most of the time it goes right through the Earth without even noticing it was there. But if you're lucky, every now and then it'll bounce off. One of these particles will bounce off an atom and do something. So if you build a very sensitive detector and put it deep underground, and why deep underground? Well, we're bombarded by cosmic rays all the time that would overwhelm any detector. But deep underground, we think all of those get shielded away, and only these dark matter particles can make it through. And then they might produce a noticeable effect, and so we might detect them directly, and there are experiments in deep mines around the world to look for it. And by the way, there's a kind of a contest, because these particles we think were created at near the beginning of time, and so we're looking at them as leftover from the Big Bang. But the other possibility is that we can create them in the laboratory with an experiment that recreates those conditions very much like the beginning of time. And there's an experiment which does that over very small regions. Of course, the Large Hadron Collider recreates over a very, very small region conditions that were similar to the very early universe. So we're hoping Other people are hoping they might actually produce this stuff in the laboratory. So there's a race between the direct detectors and the Large Hadron Collider at CERN to see who can detect this stuff first, if indeed we're right about what it is. And of course, we don't know for sure. But in this decade, we could easily know the nature of this stuff, which is very unusual, and which is responsible for our existence in large part, because you could show that galaxies wouldn't have even formed if this stuff hadn't been around. It had to collapse first, and the galaxies that we see fell into them. But 90% of the mass of our galaxy is made of this stuff, and over 40 times as much matter in the universe is in this stuff as is in everything we can see. So it's really the dominant kind of matter in the universe, and it's very exotic. But as I say, it's stuff. But the weird thing about dark energy is it's not stuff. And what I mean by that is that you could take some space and get rid of all the radiation and all the particles, so there really is nothing there, and it weighs something. And that is the weirdest thing in the world, and we don't have the slightest idea why.
Wait a second. Can you say that again?
You get rid of all of the radiation and particles and gas, so you got a region of empty space with no particles in it and no radiation, yet it weighs something. It has energy. And as I say, it turns out to have the dominant energy in the universe. There's not much in each little volume. In this room, there's not much. But when you add it up over the entire universe, it turns out, because there's a lot of empty space, there's a lot more empty space than non-empty space, it turns out that 70% of the stuff in the universe is, or 70% of the energy in the universe is dark energy, about 30% is dark matter. And the truly amazing thing, which is one of the many reasons why it seems weird to think the universe might be created for us, is that you could get rid of you and me, and of course we're not very important in the universe, but you could get rid of everything we can see, every galaxy, every star, every beautiful thing in the night sky, and the universe would be essentially the same. We're a 1% bit of pollution in a sea of dark matter and dark energy. I want to argue with you, but I want to save that argument for later about that. I personally think, you just said you want a significant award, so you can't be you can't really believe we're not significant. But getting back to this, let me get clear. So is it 30% of the matter in the universe is not yet detectable? No,
it's dark?
No, about 95% of the matter in the universe is dark energy. It's dark matter. It's not yet detectable. Matter. It's 95% of the matter. So maybe even more than that, but somewhere around 95% of the matter is this dark matter. All the visible stuff is 70%.
And 70% of the energy is dark energy?
Yes, and so 95% of the matter accounts for 30% of the total energy.
Wait, so 90% of the
matter.
There's some math I'm missing out on here.
Let me make it simpler for you. Matter accounts for about 30% of the total energy in the universe.
Right.
Empty space accounts for 70%. And of that 30%, which is matter, at least 95% of it is dark matter. The visible stuff is just a speck of pollution. It's irrelevant, except for you and me.
And back when I remember back in the 1980s when we first started hearing about, in the popular press, about dark matter, the missing matter, there was a reason that we knew that it was missing. What was the basis for inferring that it had to be there?
Yeah, well, very simple. We weighed the galaxy. We can weigh.
Simple.
It is simple.
Just weigh the galaxy.
It's really easy. Go on. You can do it in your backyard.
Sure.
With a telescope, because in fact we use gravity. I mean, how to weigh things? We use gravity, and in fact, we can weigh the Earth. In fact, this is fascinating. I don't know if I put it in the book, but it amazes me. There's a great this physicist named Cavendish who was a rich guy in England and was the first guy to measure the strength of gravity between two objects, like two cannonballs, in 1798, 100 years after Newton developed gravity. See, after Newton developed his theory of gravity, we still didn't know the strength of gravity because it's so weak you couldn't measure the gravitational force between two objects of known mass. And so Cavendish showed a way to do that. And what did he call his paper? He didn't call it on measuring the strength of gravity. He called it weighing the Earth. Even then he knew a sexy title will capture readers.
That was good.
Yeah, it was good. And the reason is because you see, you could use the force of gravity and in fact determine the motion of the moon around the Earth, but in fact you can use the motion of the moon around the Earth, the speed at which the moon moves around the Earth, to weigh the Earth, because that speed is determined by the force of gravity. And once you know the speed of the moon, then you can in fact determine the mass of the Earth if you know the strength of gravity. It's really amazing. And so that is the way we weigh the Earth today. We measure the speed of satellites around the Earth, and we weigh the Earth. Well, similarly, we can weigh the sun. I like to say in physics, it's kind of like Hollywood. If it works, you just repeat it. And if you can weigh the sun by looking at the motion of the Earth around the sun. And similarly, it turns out our sun goes around the galaxy once every 200 million years or so, and that speed of 200 kilometers per second allows us to weigh the galaxy, all the mass that's pulling us in. But we can do that for objects that are further away from the center of the galaxy than our sun. And Newton tells us that the speed should fall off because we're at the edge of our galaxy. We're at the edge of the visible mass in our galaxy. And if we're where all the stuff is, then that speed should fall off as you go further and further away. But it doesn't. Okay. But what was discovered in the 1970s and 80s by Vera Rubin and others was that looking at objects that are further and further away, their speed doesn't fall off. It remains the same. And the only way to understand that, if gravity works the way we think it does, is if there's more and more matter out there. And in fact, the speed stays constant out to 10 times as far away from the sun as we are. And that tells us that there's at least 10 times as much stuff out there than we are. And that was
the speed at which stuff was moving led us to conclude that there must be stuff out there exerting gravitational pull, to put it in crude, I'm sure, wrong terms.
No, that's right. You get an A.
But stuff that we could not detect, but it must be out there.
That's right. And you might say, well, look, it's hard to do this. Maybe we're wrong. But the thing that's happened in the intervening 30 years is we see this in every galaxy we can look at. We see the same evidence for this. And, in fact, we've been able to use, as I show in the book, in fact, with a beautiful image of something called gravitational lensing, which uses the curvature of space to weigh clusters of galaxies. And again, we find 40 times as much. Now we know directly that we can weigh these clusters, and they're the biggest bound objects in the universe. Anything that could fall into anything would fall in those clusters. And we weighed them, and we find out that there's 30% of the amount of matter needed to make a flat universe in those clusters. And so every observation is consistent with dark matter, and every time we do a new test, we find it's consistent. So the evidence has become pretty overwhelming. I mean, it's not 100%, but it would be amazing if all of these results somehow were wrong. And, you might say that, God is subtle but not malicious. I would argue if there was a God, he's probably malicious but not subtle. But in any case, the point is...
Actually, it was Einstein who said the first thing, right?
It was Einstein who said the first thing. And as I say often in the book, if it walks like a duck and quacks like a duck, it's probably a duck. In this case, hundreds of different kinds of observations all lead to the same conclusion, that dark matter dominates the mass of the universe. And it's not too surprising, by the way. In fact, let me tell you something that you may find neat, and I don't know if you remember from the book, but if you're as old as you or me, we see...
I'm definitely one of those.
Yeah, exactly. Then you will remember the days before cable television, probably.
Yes.
And the amazing thing is...
Oh, yeah, this is in the book. This is interesting and shocking. This is shocking. This is a Big Bang-related fact.
Yeah, exactly. But I'll come back to show how it relates to dark matter in a second. But it is amazing. So... you have watched on your TV the afterglow of the Big Bang, because in the days before cable, when television stations went off the air, there, of course, I used to watch it until then, there was always static. There'd be a test pattern and then static. And it turns out 1% of that static is radiation left over from the Big Bang, part of what we now call the cosmic microwave background radiation, the afterglow of the Big Bang. And it is amazing. What is amazing, of course, but the reason I bring it up is, even though it was there, television's been around since the 40s and 50s. It wasn't until 1965 that it was really discovered by people who didn't know what the hell they were doing. In fact, they lived in New Jersey, right near you, and they didn't know what they were doing.
And as I told you, I'm right now in what was the bedroom of the person who should have won the Nobel Prize that they won. But anyway, go ahead.
Exactly, because the person who had your house knew what they were doing. They didn't, but they won the Nobel Prize anyway. But they discovered it. But what I want to point out is there's nothing more visible than electromagnetic radiation. And yet it remained hidden until 1965. So it wouldn't be surprising if there's other stuff produced in the Big Bang that's a little less easy to see than light. And it remains invisible. In fact, it would be very amazing if there wasn't other stuff. And so dark matter isn't, some people think, well, these physicists, they just invent anything they need when they have a problem. And the point is that dark matter is actually quite reasonable. As my friend Frank Wilczek would say, it's radically conservative. And so,
anyway. that we think that kind of permeates space more or less evenly.
No, it's clumped where matter. Well,
clumped.
let me just say, visible matter is clumped where it is. It's also more widely distributed, but we think it's clumped because it's gravitationally attractive, and so it clumps just like matter does. In fact, it clumps more effectively.
But these things that are passing through me and you right now, if they were very big, that would be a problem if they're passing through us.
It would really be a problem. We'd really notice it. But by clumped, I mean that they're clumped around galaxies, so they're more dense around galaxies than they are where galaxies aren't. But they're still kind of a diffuse gas of these.
Still filmy.
Yes, still less than filmy, just individual particles, more like a gas.
Okay.
And their density, by the way, I can tell you their density is about somewhere around one particle per cubic meter is the density of these things as they zip through you and I.
That's about what I would have guessed, I would say.
Well, you see, you're getting an A twice today in this little.
Yeah. Now, okay, so that's dark matter. Now we move on to dark energy, and is the basic idea the same, which is that we can infer that this stuff must exist, but we cannot directly detect it.
Yeah. In this case, there's not even a hope yet that no one's proposed an experiment to directly detect it on Earth. I mean, it's here. If it's everywhere, it's here too. But the density of it is so very weak that compared to matter on Earth, that there's no hope. No one's proposed a way to look for it. But over the scale of the universe, it can build up. And now we detect it in a slightly different way, because it turns out Einstein tells us that if you put energy in empty space, then it's gravitationally repulsive. It blows. It doesn't suck. It's the only...
say that again. It doesn't suck?
It blows. It doesn't suck.
It blows. It doesn't suck. So it pushes things away from each other if you put energy in empty space?
It's like anti-gravity. And it's the only kind of energy that has that property. And what we have discovered, much to the surprise of another set of astronomers who really didn't know what they were looking for, but just won the Nobel Prize, when we look at galaxies and we measure their speed away from us, and we measure the expansion rate of the universe, it's speeding up. It's not slowing down. A sensible universe should slow down because gravity sucks. It's attractive. But what we've discovered is, in fact, it's speeding up. And there's only two explanations of that. One, the data's wrong. But in the 10 years since the data's been discovered, it gets better and better and better. Or two, there's energy in empty space. And in fact, what's amazing, you see it all fits together, is when we measured that 30% of the total energy needed to make a flat universe resided in matter, there was a problem, as I also talk about in the book, because about the same time, we discovered that the universe is flat. And so we were missing 70% of the energy. We didn't know where it was. And amazingly, totally independently, these guys discovered that the universe was accelerating, and if you try and fit their data, what do you get? If you put 70% of what's needed to make a flat universe in the energy of empty space, you get exactly what they measure, and that's exactly what we were missing. So everything...
And you conclude that God planned it that way, correct?
No, yeah, absolutely. I conclude that the non-existent God planned it that way. No, I conclude that in fact, I conclude that if it had been any different, we might not be here. But it's not so obvious of that. I mean, I actually don't conclude anything. I conclude that the universe, because of that, has the properties of a universe you might create by accident. But what it does, what I do conclude, and I think you will agree here, in fact, I'm sure you will agree, although you surprised me in the past, is that at least we know that empty space, that nothing, is far more interesting than we thought.
Oh, I totally agree.
Good. See, there we go. My first prediction of today that proves to be right.
Your first testable hypothesis.
Yeah, that's right.
Now, okay, so with dark matter, we concluded that there must be something out there exerting a pulling force by virtue of the speed of things. And with dark energy, we infer that there must be something out there exerting a pushing force by virtue of the speed of things?
That's right. And in fact, that's right. And the way you put it is kind of very nice. Because it leads you to...
Thank you.
No, I really like it. I'm going to have to use that, in fact. Because...
Too bad your book's already out, because there's a great sentence it could have.
Yeah, exactly. Well, there's always future editions, my friend. But but in any case, the reason that's interesting is it leads people... It's one of the reasons that we've been led to this weird anthropic idea. Because this energy of empty space is so weird, we don't understand it. And what's really even weirder for many people is that the energy of empty space is about the same, within a factor of 3, of the energy of matter. But if that's true, we live at the only time in the history of the universe when those two quantities are the same. Because the energy of empty space doesn't change over time, but the energy density of matter dilutes. So at earlier times, the energy density of matter was bigger, and at later times, it'll be much less. So the question is, why do we, 13.7 billion years after the Big Bang, live at the only time when these two numbers are the same? Copernicus told us, it's not supposed to be that way. We're not supposed to live at a special time in the history of the universe. Now,
and what's the answer?
Well, one answer is God could have intended that way, but the other answer is, remarkably, and it's one that you can like or not like, but the universe is the way it is, regardless, is that, remember, as you so beautifully put it, the empty space exerts a pushing force and matter produces a pulling force. So let's say the energy of empty space were, say, 50 times bigger than we measure it to be today. Okay?
Okay.
Well, then it turns out then the time when the energy of empty space would have equaled the energy of matter would have been earlier, about when the universe was about 1 billion years old instead of 13 billion years old. But what time is that? That's the time when galaxies first started to form. Now,
so we couldn't have been around then.
No, but hold on, it's even more important. If the pushing force overwhelmed the pulling force at the time when galaxies first started to form, they never would have formed. Because
we definitely couldn't have been around.
Exactly. And so people have argued, well, if there are many different universes, and in every different universe the energy of empty space is different, then only in those where it's not too different than what we measure today would galaxies form, and only then would stars form, and only then would planets form, and only then would blogging heads form.
Exactly.
So the universe is the way it is because blogging heads is here.
So that, you were saying that God created the universe the way it is so that blogging heads could exist, if I'm understanding you correctly, Lawrence.
Well, not quite. I'm saying blogging heads was created so they was formed so that they could create God to say that that's the reason they exist.
I'll settle for that. Now, here's what I don't understand is, okay, in the case of the dark matter, we say, okay, the matter must be out there somewhere we can infer its presence. In the case of the dark energy, you don't just say that. You don't just say it's out there somewhere, even though we can't detect it directly. You say it is in empty space.
It is in empty space, yes. It is in
now that's because energy, when it's only if it's in empty space that it exerts a pushing force?
You got it. Only when you put it in empty space that it exerts a pushing force.
Okay, but I still, and here I fear we may be drawn into some of the kind of conversation we engaged in last time, but to me, if space has energy in it, it's not empty.
Well, what do you mean? Let me ask you the question. What do you mean by not empty? Normally, I think, if I'd ask you, see, I love the fact that people are allowed to change their definitions on the fly in order to disagree with me. Because I think if I'd asked you an hour ago, or maybe before you read the book, what does empty space mean? What does empty mean? You'd say there's no stuff in it. There's no particles. There's nothing you can measure that's there.
Right, but energy is in principle measurable.
Well, but there's no stuff. There's no particles. There's no radiation.
Well, but Einstein told us that energy and matter are both ultimately, potentially the same thing. I mean, they're different forms of the same thing.
Absolutely, but I'm telling you, this type of energy cannot be turned into matter per se directly. I mean, it's very different.
This is a kind that doesn't obey E equals mc squared.
Well, if it did, I mean, in the sense that it's an energy that's very different than the energy that corresponds to matter, because when you have energy, Einstein also tells you, because of gravity, you produce a pressure. And in fact, matter has a positive pressure, and matter has almost zero pressure, but radiation exerts a positive pressure. The radiation pressure from the sun is, pushing things out and that sort of thing. But it turns out this stuff has negative pressure, which is really weird, and that's the reason that it blows and doesn't suck. And
okay, but are you saying anything that has just energy and no matter can be defined as empty?
Look, I'm saying I define empty to be no particles and no radiation. Nothing, just space. Now, it is true.
Well, wait, but
it is true that if space has energy, then space really is something. I'll give you that. But what I'm trying to point out is that what science has caused us to do is change our ideas of the difference between something and nothing. We used to say empty space with nothing in it. It's a good approximation of nothing. But now we're realizing that empty space with nothing in it really isn't nothing. I'll agree with you there. It's something. But what I'm trying to suggest is that the line between something and nothing is obviously getting blurred because of that. And that's just the first step of a blurring procedure, which will go on if you want and talk about more. But certainly, I would argue that the ancients' definition, and I think if you look at the Bible or look at what people might have argued was nothing 2,000 years ago, they would have said it was an infinite empty void. Empty space, darkness, but, and I think that would have been a pretty good approximation of nothing. But now you and I know better. We know that empty void is not really nothingness.
Well, yeah, we know that when we look out and it looks empty, it's not nothing. But I guess I don't understand why you want to define space that has matter in it as having as non-empty, and space that has only energy in it as empty. If I understand that that's what you're doing.
Well, because usually I think of space as a background, and I put stuff in it. I put measurable stuff in it, like matter and radiation, and I can count those things. So I think of space as a background, and I put stuff in space. Like planets or you or me.
But couldn't you put energy in it? And by the way, isn't radiation energy or not?
Radiation is energy, but it's also particles. Radiation...
And there's energy that's not particles.
And this is the kind of energy that's not particles. And I would have argued, by all definitions, can't be described as stuff. Because you can't count
so that's the... Okay, so fine. So there's a distinction there. Is it the case that most of the energy I'm familiar with and that I read about actually involves particles, and then there's a kind of energy that doesn't involve particles?
In fact,
and that's the distinction we're talking about?
You've almost got it right. You got a B+ there.
Thank you.
It's not most, but all. All of the energy that you're familiar with, every other kind of energy we know of in nature, is associated with particles. This is the only kind of energy that isn't.
And is it only that kind of energy that exerts a pushing force? Or
You got it.
Okay. Well, this is getting weird.
Yeah, exactly. That's what's so wonderful. The universe is weirder than...
I'm still... So I kind of see a basis for now saying that inhabits empty space.
Thank you.
It is a definitional thing, but at least it's a clear distinction.
Yeah, exactly. Sorry, go on.
Well, no, go ahead.
No, but...
I'm sure you were going to say something interesting.
No, you were being nice to me, so I was going to be nice to you back. I was going to say that at the same time, one could argue that it isn't that kind of nothing really isn't, is more like something. So you could make that argument too.
Yeah, because you can imagine stuff that doesn't even have the non-particular form of energy in it. That would be really empty.
Oh, hold on. No, then I don't disagree. Now I disagree with you again. If you're imagining, it's just an accident. Empty space either has energy or doesn't have energy,
right?
And that's a quantitative difference, but I don't think a qualitative one. If you're going to call one nothing, then you got to call the other nothing. But
no, I think there's a distinction there, right?
Why?
Isn't empty space without energy emptier than empty space with energy?
No, they both have nothing in them.
Well, one of them has energy, Lawrence.
Well, let me prove to you that it has nothing in it. Let me prove to you that empty space has nothing in it. Normally, if I take a region of space with stuff in it, and I double the volume, the energy density, the density of stuff goes down, right? Because the density is 1 over volume. So,
right.
So the density goes down. Now, if I take empty space which has energy and I double the volume, the energy density remains the same. And the reason is there's nothing to get diluted. There's nothing there, so it can't be diluted.
You're not saying that the amount of energy doubles when you double the volume.
I am
saying that.
I am saying that, and that sounds.
Well, then we could just say just say it is something, but it has magically self-replicative properties that are elicited when you increase the amount of space it has.
There is no magic. There's only things that look like magic.
Okay, forget the word magic.
No, but we understand why that happens. We say there is nothing there. It's not that the energy gets doubled. What happens is, and this is really strange. If your mind wasn't blown before, this is really going to do it. Because what I'm going to tell you is really strange. Because that empty space has negative pressure, it means that as it expands, the universe does work on it. The universe does work on expanding space, and it dumps more energy into that empty space. So that energy didn't come from the empty space. It came from the universe that was doing work on it.
So as the universe expands, this type of energy grows?
Yep.
That's totally mind-blowing.
It is mind-blowing.
My mind is blown.
And it's mind-blowing, but even more mind-blowing is the fact that as that happens, the total energy of the universe gets closer and closer to zero.
Now that is ironic.
It is, isn't it? Even
Yes.
even God couldn't have planned that.
If God is malicious.
Yeah, exactly. If God's malicious, and every time something bad happens to me, that's the time I begin to believe. But it is ironic, and it is weird, and it is strange, and it is stranger, I would argue, than we could have imagined. And we've been driven to that by the universe. And I think if I really wanted to say for me, the best part of the book, or the reason I wrote the book, or the reason I want people to read it, is that we've been driven to these ideas not because we're crazy or because we like to argue for or against God, but we've been driven to it because the universe is telling us it's so strange that we have to expand the horizon of what we thought was possible. And I think that's the beauty of science. That really is beauty of science.
I mean, of course, physics long ago started telling us that reality is strange. I mean, at least beginning with quantum physics. So
certainly,
this is
exactly.
more.
Well, this is like quantum physics squared. I mean, it really comes from quantum physics. But certainly, once we recognize quantum mechanics govern the universe, common sense, in the traditional sense, went out the window.
Okay, so as long as we're using this word quantum, can you explain to me? I see the phrase quantum gravity and never really know what to make of it. I never know in what sense gravity could be a quantum phenomenon. Can you just say a word or two about that?
Absolutely. Well, look, here. So, gravity as a theory right now is described by general relativity, which says it's a theory of space and time, and it's the curvature of space that we measure as being a gravitational force, etc. So space and time are the fundamental variables of gravity, if you wish, okay? Now, quantum mechanics tells us that particles like electrons and certain systems have to be treated as quantum variables, which means they act strangely. Electrons, for example, as quantum objects, are spinning in many different directions at the same time and doing very many other strange things. Now, if it is true, and we have no reason to doubt this, that quantum mechanics applies to space itself, and we don't have a theory that consistently mathematically allows us to do that yet. String theory is one possibility, but we don't know if it's the theory. But if we had such a theory, which was a quantum theory of gravity, it would be a quantum theory of space and time. And that means that what happens, the weird quantum behavior of particles would now apply to a weird quantum behavior of space. And
wait, do you mean that there would be multiple versions of the space in different, places, so to speak?
It would mean it's hard to picture, and it's hard to even verbalize. It would mean that on small scales, space could be there and not there at the same time. And moreover, just like particles pop in and out of empty space due to quantum mechanics and special relativity, if we had a theory of quantum gravity, we have every reason to suspect that space itself could pop in and out of existence, and universes could pop in and out of existence due to the laws of quantum mechanics. And therefore, in fact, that's the next stage, I would argue, of nothingness, because you might say that empty space is still something, it's still space, but quantum gravity would suggest that even empty space itself can come from nothing where there was no space at all, which is hard to picture.
Quantum gravity, is that like an aspirational theory? In other words, people are saying, well, we could possibly articulate a coherent theory of quantum gravity, or is it like already here, or what?
No, I think it's more aspirational in the sense that we have these two fundamental theories that both seem to be right. General relativity describes everything we see. Quantum mechanics describes everything we can see on small scales. General relativity sort of on large scales. and we have no reason to believe that we won't be able to merge them together in a theory which is consistent. But you're right, it is aspirational. Now, string theory, to be fair to string, well, not to be fair, to be generous to string theorists, was a big leap. It was a theory that had the potential to make a mathematically consistent theory of quantum gravity. Now, since that potential is still there, and it's still got potential, and it's but it's not it's like an assistant professor that never does anything. He had potential, but he didn't do anything. So
it's like they used to say about Brazil. It's the country of the future, and it always will be.
Exactly. And so string theory may be exactly that. It may be always the theory of the future. But at least it was a big step as a possibility. But other than that, it's aspirational. But we have no reason to believe that there should be some stumbling block except we can't do it yet, that merges these two. And when it does, it's certainly likely that the properties of quantum mechanics and gravity will produce the possibility that empty space can pop in and out of existence.
Okay, so let me just be clear. I mean, I had always heard of the long sought out, grand unification theory as unifying forces, gravity, weak force, whatever. I forget how many forces there are, but that's what I thought it was.
There are four, not three. There'd be three.
What are the forces?
If there was a trinity, there'd be only three of them. But there's four. There's the electromagnetism, which you and I are using right now. There's the strong force, which holds quarks together inside of protons. There's the weak force, which is responsible for the process of the power of the sun. And there's gravity, which is, by the way, paradoxically, by far the weakest force in nature. Even though it's the force that you and I notice in the morning when we want to wake up and get out of bed, it is by far the weakest force, far weaker than any of the forces in nature, which is why it's been so unimportant at a quantum level. It's 40 orders of magnitude weaker than electricity. In fact, Richard Feynman, who, as you know, I wrote a book about, gave a great analogy to understand how weak gravity is. Go up to the top of a tall building in New York and with a friend and push them out of the building. This is a thought experiment, by the way. Don't do this. Push them out of the building. Now, it will take gravity all of that distance, say 300 feet, to accelerate them down to the ground. But electricity and magnetism stops them in a fraction inch. They don't even make a dent in the concrete. And it's just that gravity is so weak, but the thing is it builds up over the whole Earth.
So what stops you when you hit the Earth is, you're saying electricity is the electromagnetic force?
Yeah, exactly. It's the force.
I had no idea. I thought the Earth stopped me.
But the Earth is made of atoms, and it's the electromagnetic forces of those atoms on the electrons in your body that stops you. In fact, the Earth is mostly empty space. The chair I'm sitting on and the table I just banged are empty space because the atoms are mostly empty space. But the reason they're solid is it's the electric forces that hold them together, and it's the electric forces between objects that stop them from passing through each other. So it's electricity and magnetism. It is freaky. Yeah.
So to get back to my question, this grand unified theory would unify all these forces, but now I got a second vibe from you, which is that there's also an aspiration to unify, I guess in the same fell swoop, quantum theory with the traditional conception of gravity or something?
Yeah,
I mean, that's a different dimension of unification.
It certainly is, and the reason is that three of the four forces in nature, the strong, weak, and electromagnetic, all look identical, all obey the same type of equations, and they all are understood as quantum mechanical theories.
I see.
And the only one that isn't understood as a quantum mechanical theory at this point is gravity.
Okay.
So that aspiration is double in the sense if we want to unify them, we have to make gravity quantum mechanical as the first step in some sense. And so go on.
Okay, as long as we're probably getting close to testing the patience of our audience.
Yes.
We should wrap it up for long. But as long as we're in the realm of quantum physics, I want to know how weird you think things are. I mean, I think last time you said, so the interpretation of quantum physics is that these electrons are really doing different things at the same time. Now, is it to say that? Is that to buy into the many worlds interpretation? It's not, right?
Well, it is in a sense. I mean, I'm always confused when people talk about the interpretation of quantum mechanics, because really we should be talking about the interpretation of classical mechanics, because the world at a fundamental level behaves quantum mechanically, and the classical world that we live in is kind of an illusion that's pasted on top of the reality, which is quantum mechanical. It's not the other way around. So there are certain things that are quantum mechanical that just don't have an explanation classically, or a way of intuitively understanding it. So it is one way of understanding that the electron is doing many things at the same time is what's called the many worlds interpretation, which says when I measure it, then I'll measure it doing one of those many things, and I will pick one out of an infinite number of realities that all still exist, but I'm in one of them. And every time I make an observation, the universe branches into an infinite number of different wave functions,
and literally the number of Lawrence Krauss's like grows or something, right? I mean, in the extreme version of many worlds, there really are multiple versions of us, and in some you and I are talking to each other, and in some worlds we're doing other things, right?
Absolutely. In that picture, as horrifying as it is, there are an infinite number of you and me growing every moment.
It's not intrinsically horrifying. The only thing I'm bothered by is that I'm in the particular one I'm in.
Yeah, well, that's right, and that's the problem for most people, and a lot of the New Age people who abuse quantum mechanics seem to think you can jump between these wave functions. And there
That's what I want.
And there are episodes of Star Trek where they do that, by the way, and I talked about that in the physics of Star Trek. But we are, unfortunately, or fortunately, stuck in our own wave function, and that's the way it is. And there indeed is, heaven forbid, there is a universe in which, in this picture, in which you wrote my book, and I'm interviewing you about it. It's kind of weird.
But see, there's also a version of this world where, like, I'm doing something other than talking to you right now, but everything before an hour ago that I remember is exactly the same as this version of me remembers, right?
In principle, in that picture, that's certainly the case, yeah.
And the question is, like, why am I associated with this one? Well, it becomes the question of what we mean by identity, what it is to be you. But,
you are associated with this one, but you are associated with the other one.
I wish. I mean,
you are.
I'm having a perfectly good time talking to you, Lawrence. I didn't mean it that way.
No, but it's the same you that's associated with the other one. It's just that you.
Well, how come the me that has a conception of me right now is not aware of the other me?
Well, that's because it doesn't. That other you is feeling awful that they didn't have a chance to talk to me. And so...
I'll bet they'll get over it.
Yeah, probably. But I want to point out, look, I want to point out, this sounds like gobbledygook and garbage. And the key thing is, these are interpretations of an underlying reality for which we have mathematical explanations that are accurate and explicit, and which make predictions which allow us not only to predict experiments, but build things like semiconductors that operate the computer I'm using now and the cell phone I'm using now. So it's not as if this is all just some vague quantum garbage. It's responsible for the civilization, everything that powers our civilization at the present time.
Right, it works at a mathematical level. The intuitive level is the problem.
Well, yeah, it works at a mathematical level and at a practical level. We build devices based on this stuff. And we are probably going to build devices. In fact, one of the great developments that may happen in the next 20 years is we may build devices that explicitly use this quantum weirdness called quantum computers, which are objects which actually perform many calculations at the same time, because the objects within them are behaving quantum mechanically instead of classically.
We had David Deutsch on Blogging Heads. I did not speak to him, but someone else did, and he was involved. He was involved in quantum computers, right?
Yeah, he was. I think he's taken it a step further out of reality, but that's a different issue.
Well, that's what I was going to say. I mean, his version of many worlds sounded a little like pretty literal. I mean, you're kind of half joking when you say there's another Lawrence Krauss.
Yeah.
I mean, I gather you're not totally buying into it.
Well,
but I think he was. But I think he was buying into it.
I think at some level, if you take the interpretation seriously, you have to buy into it. I guess my attitude is that I view those kinds of interpretations as a classical way of understanding something I can't understand classically.
Right. But I do think it's interesting that these quantum computers, they do force you to move a little towards a literal kind of many worlds thing, in the sense that the reason they're so fast, at least as we think of what's happening, is that this one electron is actually, the different versions of it are doing work simultaneously. That's the source of the power, right?
Well, it's not work. They're doing computations. So they're doing work.
Well, that's what I mean. Computational work. I don't mean in the Newtonian sense of work, but
They're doing many different computations at the same time, and that you're right, and that is weird but true.
Mm-hmm.
And it is,
Well,
and it is, and it could be that quantum engineering, if you want to call it that, will become the new technology of the 21st century. Either that or biotechnology. I don't know which will take over, but one or the other is likely, and they may be both, and they may become the same thing, because it could be that in some sense biological systems can be used to do that too. But that's even a farther stretch of the imagination.
And I think we freaked people out quite enough today, Lawrence, without getting into that.
Yeah, I think you're right. I think I couldn't have said it better.
So, but there is, that does mean there's more to talk about. Should we do this again?
I'm enjoying myself. I don't know if you are, and I certainly don't know if
I am. I like being freaked out. And
then let's do it again. Let's do it again.
Okay,
sometime.
so congratulations again.
And
The
thanks.
Universe from Nothing. The real book looks sexier than the Bound Galleys, I assure you. Although the Bound Galleys have a nice old-fashioned kind of authority to them.
Yeah, they do, but there's nothing like the real thing, as they say, even if the real thing is an illusion. Yeah,
right.
Anyway.
Exactly. So, New York Times bestseller, thanks entirely to Blogging Heads, although I suppose slightly to the author.
Thank you.
And I'm happy that we've done that for you, Lawrence.
Thank you. I'm eternally grateful in all the universes in which I can be.
I speak for all the Bobs when I say, "Aw, shucks, it was nothing."
Okay, thanks.
All right.
Okay, you take care.
Okay, so we'll see you next time.
We'll do it again. It's a pleasure. It was great. Take care.
Same here. Okay.
Bye-bye.
Take care.
Bye-bye.
Bye-bye.